and welcome back to our series on ANOVA. Today we're going to talk about doing a randomized complete block design in R. Now, the data we're going to use is the seeds data, which is available online, and I'll put a link up to this at the end of the video. Now, I've read my seeds data in, and this is what it looks like. Now, notice I have a control, I have treatment A, treatment B, treatment C, and treatment D. I have my locations. So what we have here are 10 locations in Virginia, 10 different counties in Virginia, and we're going to have our yields over in the first column. Now, the first thing we'd like to do is create a plot of the data. So let's first create a box plot of just our yields and our treatments. And here we see we've got A, B, C, our control, and D. Notice our control seems to have a higher yield than any of the others. Well, now let's plot against our blocks. So when we plot against our blocks, notice we get each of our counties in Virginia a box plot of the yields by counties. So we're going to set our hypothesis for our randomized complete block design. Remember, our null hypothesis, mu I equals mu j. Our alternative hypothesis, mu I does not equal mu j. And we're going to choose an alpha of 0.01. Now, recall also, Yij is the observation treatment I for block J, and TRT is going to be our number of treatments. Well, here we have a number of treatments as 5, and we have 10 blocks. So B is our number of blocks, and that is 10. So what is the first thing we need to do? The first thing we need to do is find our grand mean. Remember, that's 1 over the number of treatments times the number of blocks times the sum of the Yij's. And so that's going to be 1 over 5 treatments times 10 blocks times the sum of our first column. Well, as we can see, y bar dot dot then will equal 457.1008. But we can simply take the mean of the first column, and we'll see that we should still get the same, 457.1088. Now, we need to find our individual treatment means and standard deviations. And so y bar I dot, remember, is 1 over the number of blocks times the sum of the Yij's. Here we're summing across the blocks. And so we get 1 over 10 times the sum of the Yij's. Now, what we can do, let's look at our control group. Here I'm just going to find the mean for the control group. Well, y bar 1 dot is going to be the sum of the seeds. Well, they're going from 1 to 10 in the first column, and I'm dividing those by 10. And so y bar 1 dot then should be 612.897. Well, let's see. If I simply find the mean of the first 10 rows in the first column, then what I get for y bar 1 is 612.897. And I'll do the same thing except with the standard deviation, SD1 dot. And then that's going to give me 56.83247. Now, I'm going to go ahead and run the rest of these. Now, I need to find my mean and standard deviation for my blocks. Remember, y bar dot j is 1 over the number of treatments times the sum of the yi's. So we're summing across all the treatments and then divide by how many treatments we have. Y bar dot j then, well, we had 5 treatments times the sum of the Yij's. Okay, so the first thing I'm going to do, because we've got so many areas, notice Albemarle, Amherst, Augusta, Buckingham, Floyd, Halifax, Lee, Nelson, Rockingham, and Sussex. I want to subset my data from my block based on Albemarle. And then I'm going to select the yield and the treatment here. And so block 1 is simply going to be the values for Albemarle. And so notice what I get. Here's my value for Albemarle in control, and then for A, B, C, and D. And now I can simply take the mean of these values, y bar dot 1. So my first block mean is 430.158. And I'll do the same thing with the standard deviation. And then if we come down, I'll do a second example. Block 2, I'm going to subset my data based on the county Amherst. And when I do that, I'm going to select the yield and the treatment. And so notice block 2 is all my values for Amherst. And then I'll simply take the mean and the standard deviation. And now I'll run this for the remaining locations. So I need to find sum of squares treatment. Remember, that's the number of blocks times the group mean minus the overall mean squared. And I'm going to sum these up. So I get the number of blocks. Well, here is group mean 1 minus the overall mean quantity squared plus group mean 2 minus the overall mean quantity squared, etc., etc. So it's B times the sum of squared deviations of y bar I dot minus y bar dot dot quantity squared. When I run this, what I get for a sum of squares treatment value, 472,826.4. Well, now we need to look at the sum of squares for the blocks. Remember, sum of squares blocks is the number of treatments times the sum of squared deviations for the block means minus the overall mean quantity squared. So I get my number of treatments times, well, here's y bar dot 1. This is block mean 1 minus overall mean quantity squared plus block mean 2 minus the overall mean quantity squared. And we do this for all 10 blocks. And so if we run this, that we get a sum of squares block 16,497.48. Now I need to find sum of squares total. Well, this is easy. Sum of squares total is just the sum of the yij's minus the overall mean quantity squared. And so when I run this, my sum of squares total I find to be 575,320.1. And now all that's left is to find the sum of squares error. Well, recall, sum of squares total is sum of squares treatment plus sum of squares block plus sum of squares error. And so sum of squares error then is just going to be sum of squares total minus sum of squares treatment minus sum of squares block. And we'll run our sum of squares error, 85,996.2. Now let's find our degrees of freedom. Degrees of freedom of treatment is number of treatments minus 1. Degrees of freedom for blocks, number of blocks minus 1. Our degrees of freedom for error is our number of blocks minus 1 times our number of treatments minus 1. In other words, degrees of freedom for block times degrees of freedom for treatment. And then degrees of freedom for total is number of blocks times number of treatments minus 1. Okay, so now that we've got this run, let's calculate our mean square for treatment. Mean square treatment is sum of squares treatment over degrees of freedom for treatment. So our mean squares treatment, 118,206.6. Mean square block, sum of squares block over degrees of freedom for block. So our mean square block now is 1,833.053. And then our mean square error, our sum of squares error over degrees of freedom for error. So our mean square error here, 2,388.783. Well, once we've got all these calculated, we're then going to calculate our F value. Remember, our F value is mean squared treatment over mean square error. Our F value then can be seen to be 49.48402. Now notice I have not calculated an F value for the blocks. Remember, we're blocking because we know there are differences. And so there's no reason to calculate the F value for the block. We're not going to test it. If I were to calculate the F value for the block, I would simply do mean square block over degrees of freedom of error. Now, let's find the probability that our F is greater than the F value. So notice I've got the probability of the F. My first value is my F value. My second value, degrees of freedom for treatment. My third value, degrees of freedom for error. Lower dot tail should be false. Let's see what we get. 3.802019 e to the negative 14. It's quite a small p-value. We can do this, and our algebra will work. However, it's much easier to simply do an analysis of variance. So we can use our ANOVA function. But keep in mind, we said that we're going to be dealing with the simplest type of randomized complete block design, and that there will be no interaction between block and treatment. And so what I have here is my yield modeled by treatment plus location. Notice there is no interaction between these two. This is simply the additive model we discussed in our last video. And so I've got my linear model statement nested inside my analysis of variance statement. And if I run this, 4 degrees of freedom, 9 degrees of freedom, 36 degrees of freedom for treatment, location, and residuals, respectively. Our sum of squares, well, let's compare. Our sum of squares for treatment, 472,826. Our sum of squares for block, 16,497.48. Our sum of squares total, and then our sum of squares error. And notice our sum of squares error, 85,996.2. So now what about our mean square treatment and mean square error? Well, let's look at mean square treatment, 118,206.6, 118,207. Mean square block, 1,833.053, 1,833. Mean square error, 2,388.783, 2,389. Our F value for our treatment, 49.48402. Now notice, the ANOVA statement gives us an F value for our location. It also gives us a P value for our location. However, we're not concerned with this P value because we're blocking based on differences. We know there are differences in the soil, or at least we suspect there are differences in our different locations in perhaps our soil nutrient quality. And so we're not going to worry about whether we've got a significant or an insignificant F value for our block. But we are going to worry about this value. This is our P value for our treatment. And what did we say we got? 3.802,019 e to the negative 14, 3.802 e to the negative 14. So notice these are similar. These two values that we get in our ANOVA and with our algebra are the same. So what does this tell us? Well, let me rerun this ANOVA statement again. What this tells us is that it looks as though we do have differences in our treatment. Now, the question may be, where might these differences lie? And as we saw in our analysis of variance, where we did multiple comparison tests and used Tukey's, we could do a Tukey analysis. And what we would see, notice all of these are just looking at differences here in location. So let me highlight these for a minute. We don't need any of these. These are looking for differences in location. We're not concerned with that. But what we are concerned with are our differences in our treatments. And notice what we have here. D and A are similar. B and A, C and A, control and A, B and D, C and D, control and D, control and B, and control and C are all different. However, C and B and D and A are similar. So D is similar to A, C is similar to B. One of the things that we might like to do is create confidence intervals for our means. So we need to find our critical t value at alpha over 2 and our degrees of freedom of error. In our current example, alpha is 0.01, and so alpha over 2 is going to be 0.005, and we'll use the qt function. Notice I've got lower tail equals false, so I want the probability above this value to be 0.005. And so my t with alpha 2 degrees of freedom, error 2.719485. And now I need to find standard error for my treatment means. Well, the standard error, I'm going to call this for treatment means, I'm going to call SY bar I dot is just the square root of the mean square error over the number of blocks. And so SY bar I dot is going to be 15.45569. Now that I've found the standard error for my treatment means, I can create my confidence intervals in the following ways. Take your group means, add and subtract your critical t value times the standard error for the treatment means. And so when I look at the confidence intervals for my first group means, I get 570.865 to 654.9285. And when I look at my second group, I get 292.9095 to 376.9725. When I look at my third group, I get 428.5245 to 512.5875. My fourth group, 449.8215 to 533.8845. And my fifth group, 333.2255 to 417.2885. Now, let's then suppose that I'd like to look at the variation in the differences. And I'll call this SD bar. Well, that's just the square root of twice the mean square error over B. And so for standard deviation of our differences in groups, 21.85765. Okay, that's it for now.